research at Harvard University. In 2012, Professor Ristenpart co-developed AIChE, the design of coffee, which is now the most popular elective general education course on campus, taught over 1,500 students per year. His research expertise in his complex transport phenomena, with the current research supported by the Specialty Coffee Association, focusing on convective and diffusive mass transfer effects during brewing of coffee and their corresponding impact on quality. Please welcome Professor William Ristenpart.
Okay. Wow, okay. So I was impressed by the Jeopardy yesterday, and I thought I will give a little bit of a more detailed lecture, if we have time, thinking about specifically mass transfer during coffee brewing. Okay? So does that sound good? You guys want to do this? Okay, all right, here we go. All right, so first, a little bit about University of California, Davis. Here are the Estados Unidos. Okay, so Davis is located in California, very close to San Francisco. Okay, and these are all the airplane flights. There are no direct flights to Medellin. Okay, but we're in the middle of the Central Valley, and this is what Davis looks like. Okay, so it's in the middle of the Central Valley, very flat, very large, 28,000 students, more than 6,000 graduate students, and many, many bicycles, bicicletas on campus, and many, many Spanish-speaking students. I have many estudiantes, hablan español. And you might know a little bit about the University of California. There's UC Berkeley, UC Los Angeles, UC Santa Barbara. UC Davis is the only one that has food science. Okay? And so there's a tremendous emphasis on food at Davis. And so, and two of my favorite beverages already covered. There's a whole department of viticulture and enology. And those are the words that mean uvas, growing grapes, and making vino, wine. So whole faculty just for that. There's also food science and technology, and that's where they study beer. And so there's a whole very popular program on beer. And so here are some pictures of where this takes place. This is the Robert Mondavi Institute. Mondavi is a very, very famous maker of wine in Napa Valley. Okay? And so we have a beautiful facility that has a vineyard, has a winery, it has all these cool things. And here's a floor plan of one of the buildings. And so this building right here is the pilot winery. And so it's got a beautiful facility for making wine, fermentations. It's got a pilot brewery. It's got a pilot food processing facility. I mentioned this yesterday, this LEED Platinum. This is in terms of sustainability. This facility was the world's first LEED Platinum certified food production facility. So usually LEED is for offices or homes. This is a food production facility. And so it costs a lot of money, and now it's used by dozens of faculty, many students every year. And for coffee audiences, for people who care about coffee, I point out that none of this, even though it's brand new, none of it is dedicated to coffee, okay? And the reason for that is historical. So coffee historically has not been studied academically in the United States. And the reason is that coffee is not grown in the United States, very, very little coffee. And so without agriculture for coffee, there was no government support for coffee. Without government support, there was no professors, no academics, no classes, nada, okay? And not just Davis, nowhere in the Estados Unidos is there coffee science. So, and that's what leads up into the question I asked, like, what does coffee have to do with chemical engineering? Okay, and so I'm a chemical engineer, you guys are chemical engineers. And so my colleague, Professor Tanya Kuhl, and I, almost 7 years ago now, we had an idea. And the idea was, can we use coffee to teach chemical engineering? Okay? And back then I knew very little about coffee. I just knew that I drank a lot, but I was very curious about it. Okay? And here's the main question. What does chemical engineering have to do with coffee? Right? And this is actually the first picture we show to our students. And we show them this, a picture of green coffee beans, and you do something to it, and then eventually it becomes a cup of coffee. And you guys as chemical engineers know, like, what do chemical engineers do? You design ways to convert raw materials into a desired valuable product. And if you think about what happens in this process, everything in the chemical engineering curriculum, all the things that you study, can be found in coffee, okay? And so presumably you take classes in transport phenomena, so that's how fluids move around, how heat moves around, how molecules move around, okay? That happens in coffee. Thermodynamics, you have to roast the coffee, you have to heat up the water. There's thermodynamics, okay, in coffee. And then what makes chemical engineers special is that we understand chemical kinetics. And there are lots of very complicated chemical reactions that take place both in roasting, tostadora de café, in the roasting, as well as in the brewing, the extraction, okay? And so all of these things that you study in chemical engineering are crucial for coffee. And so we had this idea, and we introduced a course called AIChE, that's Engineering Chemical 1, the design of coffee. And these are pictures of our laboratory where we teach this class. And the way it's set up is we have 1 hour of lecture per week and 2 hours of laboratory exercises where the students get to roast coffee, they get to brew coffee, and do experiments and learn about core chemical engineering principles. And so here's a picture of our book. It's on Amazon if you want it, okay? And the way the course is organized is in 2 parts. We're on the quarter system at Davis, so we have 10 weeks. And so the first 6 weeks, we illustrate core scientific principles associated with coffee. And so, for example, we talk about conservation of mass. We talk about conservation of energy. We talk about chemical kinetics and pH in reactions. Okay? So we do those experiments, and then we switch to a design competition where the students compete to make the best tasting coffee using the least amount of energy. Okay? And so, and that's a lot of fun. We make it like a contest. It's an optimization problem. We're trying to maximize something and minimize something else. Okay? And so if you know all the steps for making coffee, if you talk to somebody in the coffee industry, this is the picture that you might have. Okay? So you start with your raw material. For us in Los Estados Unidos, this is what we have, because we don't grow it. You guys grow it here in Colombia, and then send us these things. And then what do? We roast them. We have little benchtop roasters. You store them, you grind them, you brew them, and then finally you have your cup of coffee. And so this is how a normal person looks at the process of making coffee. And how does a chemical engineer look at it? It looks like this, right? So here's the same process. Okay? This is a qualitative process flow diagram for making coffee, right? Exactly the same process. And a lot of the words that we use in chemical engineering are here. So the roaster is actually a fluidized bed reactor. Okay? The coffee pot itself is also a reactor. After you brew coffee, there's lots of complicated chemical reactions continue to occur. That's why the flavor of coffee changes with time as it sits there. Okay? And we do things like this. So we, lab 1, we reverse engineer Mr. Coffee, right? And it's a great little experiment. The question we ask the students, you put the water in to here, so the water is right here, but then you turn it on and the water starts pumping out here. So the water goes from this height up to this height. So very simple pregunta, what makes the water move? Why does it move? And so you take it apart and you try to understand why it moves. And usually students, their first guess is, there must be a pump. There's a pump in there somewhere. And you open it up and there's no pump. So then you have to think more carefully about it, okay? I'm not gonna go through all the labs, but just to show a few, here's the one based on conservation of mass, right? And so here's a control volume. And here, it's really a great example because you can show how to derive a predictive equation using the principle of conservation of mass. And you can also show how to correlate or do linear regressions of experimental data and fit that to a model. And the thing I think that gets a lot of people very excited is that coffee can have amazing flavors, right? Coffee doesn't just taste like coffee. This is a review of a particular coffee from somewhere in Africa by somebody who's very famous in California for specialty coffee. And I won't read the whole thing, but here are his description of the flavor of the coffee. It's got words like dried wildflowers, red honey, caramel candies, floral, citrus, orange blossom florals. My favorite one is pineapple upside down cake. Do you have that here in Colombia, pineapple upside down cake? Okay, it's a very weird thing to describe coffee as tasting like. Okay? And when I first learned about this type of description, I thought it was all nonsense. I thought it was just marketing silliness. But it turns out that coffee can have these flavors. And I've tasted them, they're possible. And so there's something called the coffee taster's flavor wheel. So if you zoom in, you can see that these are all the different types of flavors, sabores, that can be present in coffee, right? And there's good ones that you might want. Chocolate, I don't know how to say peanuts in Espanol. All the fruits are over here. I'd like to point out that this work, the statistical work for this plot was done by one of my students. This is Molly Spencer. She got her PhD in food science, and she published this on the cover of the Journal of Food Science, which is really awesome if you're a food science student. Okay? And now in specialty coffee circles, you see this flavor wheel everywhere. So these flavors are possible in coffee. As chemical engineers, the first thing you should think is why? Why are these flavors here? Well, that's because when you're drinking coffee, what are you drinking? You're drinking molecules, okay? And so there are different molecules present. And coffee is really, really complicated, muy complicado, okay? And so here's just one example of certain chemical reactions. And so, do you guys know what this is? What is this? Oh, bonus points, bonus Jeopardy points. What molecule is this? Anybody know? What did you say? Did you say some kind of sugar? Very good. This is sucrose. So the white powder that you put into your coffee. How many people had coffee this morning? Okay. Did you put sugar in? If you were putting in sugar, you were putting in this. This is sucrose. Okay. And when you take a green coffee bean by mass is about 10% sucrose. So these green coffee beans are 10% by mass sugar, okay? And when you roast, when you put them in the tostadora, okay, many different chemical reactions. These are just broad classes. So you have fragmentation reactions where the sucrose breaks apart and it forms things like formic acid and acetic acid. Conoce acetic acid? Huh? Oh, vinegar, very good, okay. No sé la palabra en español, okay. Yeah, so vinegar, okay. There's literally vinegar. When you drink a cup of coffee, there's vinegar in there as a consequence of roasting. There's also dehydration reactions. This is where you rip out a water molecule, and it forms things like hydroxymethylfurfural, okay? Big complicated name, but that's a flavor molecule associated with caramel, caramel, okay? So that's, you know, browning reactions for caramelization. And then very important is a class of reactions known as Maillard reactions, okay? And this is where the sucrose combines with proteins to form really big, complicated molecules. This thing is a type of molecule known as a melanoidin. They're big and they're brown. And Maillard reactions happen in many things, including steak, beef steak, okay? So when you brown some beef, you also have melanoidins, you have reaction products. Those are also there in coffee, okay? And so there's lots of examples. I could go on for all the different things we teach in the class. When I was introduced, they mentioned that we have now, it turns out that students really, really like coffee. So this is the number of students per academic year in a couple classes. The blue is what used to be the most popular class. It was about beer. You can see the trend there. I started the class for coffee in 2013 with 18 students, and now it's up to 1,500 students per year. So students really like coffee. They like doing experiments and learning about coffee. Okay. And this is my very favorite slide. This is the student newspaper, and every year the students vote on what's the best restaurante, what's the best bar. They also vote on what's the best GE, general education course. And so this year when they voted, their favorite general education course was design of coffee. Number 2 was introduction to human sexuality. Number 3 was introduction to beer brewing. So at University of California, Davis, coffee is better than beer and sex. Okay. Yeah. But so I got into this as a way of teaching. I got into coffee because I wanted to teach about chemical engineering. But very quickly, going back to what I was saying earlier, it became very clear that the coffee industry in the United States had huge unmet needs in terms of science and education. There's nowhere doing academic research on coffee. And so in terms of kind of a timeline, in 2013, I developed my class. Some of my colleagues and I started getting together in 2014. In 2016, we received a founding gift from Peet's Coffee, which if you ever go to the west coast of the United States, Peet's Coffee is really good coffee, okay? Very big coffee company there. And since then, I've been working a lot with industry to receive donations. And what we're doing is we're raising funds for a building on campus. And so there's a whole building that is now the home of the UC Davis Coffee Center. Okay? It's very close to the Robert Mondavi Institute, right across the vineyard. And the idea for this building is to have everything you need for advanced coffee science and education under one roof. And so there's a whole bunch of different spaces. There's a green bean storage laboratory. So you guys know that the flavor of wine, of vino, changes as it ages, right? Coffee does too. Green coffee, the taste changes as you let it age. And people don't really understand it at all. So we have a whole laboratory dedicated to that. Peet's named our pilot roastery, so we're going to have a whole room just for our coffee pilot roastery. La Marzocco, they manufacture espresso machines, so we have a whole brewing and espresso laboratory, a sensory and cupping lab, a chemistry lab, innovation space, classroom space, and outside a greenhouse. So again, everything we need for coffee science and education under one roof. And there's many different companies that have come together. People in the coffee industry would probably recognize some of these more than others. Okay. And I've been spending a lot of time in architecture lately. We hired a really, really good architecture firm that's designing this stuff. Architects like to do things like, they like that flavor wheel, so they're going to paint a big flavor wheel on the floor and halfway up the wall. And so here's some renderings, ideas to make it really beautiful, and have it be a place where people, anybody from around the world, including, I hope, Colombia, who wants to come to the Estados Unidos and learn about coffee science, this will be the place they can come to, okay? And learn about rigorous, for example, sensory descriptive techniques for tasting coffee, and be able to hang out with academics from around the world focused on coffee, okay? And so I should emphasize that, I'm a chemical engineer, but one of the strengths of a university is you have professors from all the different departments, okay? And so these are all professors who are in their own departments, but they're interested in coffee. And I'll point out a few of them. Professor Juan Medrano, he's de Guatemala, now he's in California. He's one of the first ones to sequence the genome of Café Arabica, the DNA. So he and his team did that. Erwin Donis Gonzalez is also from Guatemala. He's a biological agricultural engineer who is, his expertise is in drying of agricultural products, like coffee. And there's many other people on here, I won't mention all of them, okay? But we have everything from the DNA to the final sensory and consumer science, how you perceive things, okay? And we're setting everything up to be able to answer many different scientific questions about coffee. There's a long list of things. I could give a whole talk about many of these different questions that different people in the Coffee Center are currently studying. So that was all a very long way of saying, what does coffee have to do with chemical engineering? I got into it because I wanted to teach, okay? But now it's grown into something much bigger. But since you guys are chemical engineers, I thought we should talk a little bit about mass transfer. Who here likes mass transfer? Oh my gosh, only one? Solo uno? I like mass transfer, I like it a lot. So what I'm going to do now is share a little bit about how do we teach first-year college students, all right, the freshmen, so 18-year-olds, how do we teach them about mass transfer? Because usually that's a more advanced topic that you don't think about until later on in the curriculum. And well, the way we teach them is by using coffee, right? So I'm going to share with you slides that we show the freshmen. And so if you already got an A+ in mass transfer, all right, you might already understand this stuff. So you can think about how do we use this to teach. If you did not get an A+, then maybe you learned something here. Okay. And now, if we have time and if there's interest, then I can switch into an even more detailed model, okay, so that we can do a little calculus. And I guess I'm leading a workshop this afternoon. Is that still happening? Yeah, and so we're going to test some model predictions. We'll compare a model versus some theory, versus some experiments. So let's get into it. So here are slides that we use to try to illustrate mass transfer, all right? And so the very first thing we do is just give a very simple definition. When you hear the phrase mass transfer, what does that mean? That means chemicals, molecules, moving from here to here, moving from one place to another. And one particular type of mass transfer is extraction, also known as leaching, okay? And that's very specifically mass transfer from a solid to a liquid, okay? For example, from coffee grounds to water. Or in this example, we have tea. I don't know, is tea very popular in Colombia? Do people drink más o menos? Okay. Well, you can imagine this experiment, right? So it's hard to see here, but there's a beaker, okay, filled with water. At time equals 0, you drop in a tea bag, and extraction begins. And then what happens as time progresses? The water becomes darker, okay? And so here's a very simple question, right? How do we make the tea stronger, right? How do we get more of this brown stuff into the water, okay? All right, and so to answer that question, we have to think about this word flux, okay? All right, and so do you anybody, you guys recognize these photos? The Americans do. Do you recognize? Okay, you guys are old enough. Do you guys recognize these photos? I'm curious. Back to the Future, have you guys seen that? Okay. When I show this to audiences in the United States, all the old people start laughing. The 18-year-olds, they haven't seen it. They're like, oh, what is this? I don't know. Okay. So, yeah, so the reason I put these pictures is that in Back to the Future, they travel through time because they have a flux capacitor. You guys remember the flux capacitor? They had to have so much plutonium, and then it had to go 88 miles per hour. All right, so why did they have a flux capacitor? It sounded scientific-y. It sounded fancy. It doesn't mean anything, okay? So that's not what we mean by flux. Flux has a very precise, real definition, okay? And specifically, it's the amount of stuff per unit area, per unit time. So amount of stuff per area, per time, okay? And the stuff, in this case, is molecules. We want to count how many molecules per unit area, per unit time. And so back to our question, how do we maximize the strength, okay? Well, we can look at this definition of flux and think about it. What we're asking when we maximize the strength, we want to have the total number of moles of stuff, how much brown molecules in our tea, We want that to be maximum. So we rearrange this dimensionally, and that's going to be the flux times the area times time, okay? And so to make it as strong as possible, we want to maximize the flux, we want to maximize the surface area, we want to maximize the extraction time. So let's go through those, okay? And so the first thing is like, well, what does the flux depend on? And as you learn in your mass transfer courses, well, it depends on a concentration gradient, a difference in concentration with respect to position. And so early on, next to our tea bag, we have a very high concentration of solid phase molecules right there next to the tea bag. And out here it's zero, nothing. So we have a huge concentration difference, and that means there's going to be a huge flux, molecules per unit area per unit time coming out. And then as time progresses, what happens? Okay? Well, eventually in the liquid phase, we have a higher concentration. And as we have a higher concentration, now the concentration difference is smaller and the flux becomes smaller. Okay? And so the word puny means really, really tiny. So puny concentration difference, puny flux. Okay? And so to think about it a little bit further, here's a cartoon model. I'm sorry, I can't read this very well. But these big circles are supposed to represent big coffee grounds. These little orange circles are supposed to represent molecules. And the idea is that if we have a lot of molecules here, we have a high concentration. Very few molecules, we have a low concentration. And the flux can be characterized in terms of this. We had this on Jeopardy yesterday. A mass transfer coefficient, K, times C near minus C far. That's the concentration difference. C near is the concentration here. C far is the concentration somewhere far away. And so K is the mass transfer coefficient. And what is it? It really is a measure of how fast the molecules can move, okay? And so it's a measure of how fast the molecules can move. And so it depends on a whole bunch of things. In general, if the molecule is big, okay, a big molecule, right, it's very slow. So bigger equals slower. It also depends on the temperature. The higher the temperature, the more energy the molecules have, the faster they move. Okay? And what makes things really complicated is it also depends on how fast the fluid is moving. So if you mix it, if there's convection, all right, the molecules move more quickly, and K, our mass transfer coefficient, is higher. Okay? And so to explain a bit more about temperature, and again, I think hopefully this audience is familiar with these ideas. If you're freshmen, you haven't thought about this before, but you know, molecules, if you zoom in, they're bouncing off of each other, okay? And the higher the temperature, the more vigorously they're bouncing off of each other, okay? And so K is large for small molecules and when the liquid is hot, okay? Okay, so that's the mass transfer coefficient. This next one, C near, this is the concentration near the solid. And this is also related to the solubility. So solubility is the word that we mean to describe how easy it is for these molecules to move from the solid phase into the liquid phase. Okay? And this also depends on the molecule. It depends on how big the molecule is. In general, big molecules are not very soluble. Small molecules are more soluble. Okay? It also depends on temperature. Okay? And so solubility, just in terms of defining this a bit more, again, back to our sugar. This is a great example. If you drop a sugar cube into coffee, what happens? It starts off in solid phase, and then you mix, and then what happens? It disappears, it's gone, right? It's dissolved, it's become solubilized. Okay? And so that's an example, if you just use a little bit of sugar, of complete solubility. You start with one phase, you put in your sugar cube, now you have two phases, you wait long enough, and you have one phase, which is now a solution. Okay? Here's the opposite limit, here is insolubility. Do you guys have Twinkies in Colombia? Can I say Twinkies? The Americans know it. You guys, what is it? Sus Marinos. Okay, well, if you ever go to the United States, go to the grocery store, you can get a Twinkie, okay? They're very bad for you, okay? If, gordo, muy gordo, okay? All right. But if you take a Twinkie and do this experiment, take a cup of water and put the Twinkie in, okay? It doesn't matter how long you wait, the cellulosic material in the Twinkie never dissolves, okay? I mean, eventually it melts into kind of a puddle, but it never goes in the solid phase. And you get this kind of disgusting thing, okay? And so a key point is you have a uniform phase at the end when something is soluble. I recommend, what was the name of that? Submarine, yeah. So maybe we try that with submarine. Put it in some water and see what happens, okay? Okay. Solubility also depends not just on the material, but also the temperature, okay? And so this is a plot of the amount of solute, okay? Solute means the stuff, the solid phase that goes into solution, all right? The grams of solute per 100 grams of water. And this black curve here, that's for sugar, sucrose. And it's plotted versus temperature. And you can see that if you want to get more sugar into your water, you want to go to higher and higher temperatures. And bartenders know this. This is how you make simple syrup. How many of you guys like cocktails? ¿Te gusta cocktails? Mucho me gusta cocktails. Okay, well, so many drinks need sugar in the water, right? And so you heat up the water, you can get, and look at it, you can get 500 grams of sugar into 100 grams of water. That's a very, very thick syrup. The red curve is salt. Different material. It's also a white powder, but very different chemical composition. It's almost independent of temperature. Okay? So this is part of the complexity of coffee. Coffee is composed of thousands of different types of molecules, and they all have different solubilities, and they all have different temperature dependencies. Okay, so anyways, that's the solubility. That's related to C near. The last thing here that defines our flux is C far, and that's the concentration far away from the surface of any solid particle. Okay? And this really kind of measures how much space or room is available out in the liquid. Okay? And so what does that mean? A good example is old-fashioned percolators. I don't know if you ever had those in Colombia. Yeah, okay, good. So about 50 years ago, this was the main way that people made coffee. And how did they work? You put water at the bottom, coffee grounds up here, heated it up, water would drive up through here, and then drip through here, and then it would come back down. But the key thing about a percolator is it would continuously keep doing that, okay? And so if you think about the percolator, initially the water is empty, so C far is 0, and that means you have a very large concentration difference. So the first water that comes through, C is empty water, and big flux. Okay? But then as you continue to boil it, now it starts turning brown. C far, okay, gets bigger and bigger. And now what's happening is that you've already extracted all the smaller molecules, and now you're giving more time for the bigger molecules to come out. It turns out that many of the bigger molecules are more bitter. Okay? And so when you make coffee with a percolator, you tend to get extremely over-extracted, very bitter coffee because of this reboiling action where you're basically passing already brewed coffee over the coffee grounds. Okay, so that was a long description of flux. And back to our original question, how do we maximize the strength? Well, we maximize the flux, taking advantage of all those things I just mentioned. The next one is easier. We want to maximize the surface area. And the surface area of what? The surface area of the coffee grounds. Okay? And so I think probably everybody has an idea that when you grind coffee, you can make it either very coarse, very big, or very fine, very small. Okay? And so if it's very, very fine, then you have a very, very large surface area. If it's very coarse, you have a very small surface area. Okay, and so hopefully we can have some examples in the lab. In my lab, we have lots of examples, okay, of grinding to different sizes. And there are many different brewing techniques, all of which are supposedly optimized for different grind sizes. So all the ways from very, very coarse, okay, for commercial like auto drip and French press. I think we have French press. Typically use a very coarse grind there. All the ways up to espresso. Espresso has a very fine grind. Or Turkish coffee. ¿Cómo se dice Turkey in español? Turkey. Okay, yeah. So in Turkey, if you get to go to Turkey, all right, they grind their coffee the finest probably anywhere in the world, and it's very, very fine grind, very thick coffee. Okay. The last thing we can optimize is the extraction time. So if you brew it longer in time, then it's stronger. Okay. And so, but let's think a bit more about how that looks. Here's a qualitative graph. Right? Again, here's our pictures. Here's the concentration versus time. And in general, it increases rapidly, and then it plateaus. Okay? It plateaus as you get to a smaller and smaller concentration differences. And so if we zoom in on one coffee ground, and we make it a square, just to make it simpler to draw, and think about the concentration versus position versus distance, okay? At some early on time, what do we have? We have our solubility concentration, right at time equals 0. And then as time progresses, we have molecules moving out into solution. And so each of these curves represents at a particular time what the concentration looks like versus distance. And so far away from the coffee ground, it's still 0, but close to it, the concentration is getting higher and higher and higher. And so the reason I emphasize this is like a very important question is, what does mixing do? When you mix your French press, okay, when you stir your coffee, it's going to extract more quickly. And why is that? Well, basically what you're doing is disturbing these concentration gradients. So here, let's imagine you pour in the water, you let it sit, you have a concentration gradient that looks like this. And now at this point in time, okay, now you start mixing it up. All right? Well, what happens? All these molecules that are here get displaced and moved around, mixed everywhere. And so after you mix, now it looks like this. And so you had a very high concentration here, 0 concentration here, and then after you mix, it's the same smaller concentration everywhere. But now when you think about it, what has that done? At any particular point along here, you had a small concentration difference. Okay? At any point along here, the slope of this line is the concentration gradient. You had a small concentration difference. Now after mixing, look what you've done. You still have the solubility concentration right there, and now again you have a big concentration difference. Right? And so by making that big concentration difference, now you increase the flux again. Okay, so that's a little bit about just extraction and mass transfer in general. Now let's focus on coffee in particular, okay? And so here's a cartoon of a green coffee bean. And the thing about coffee is that it's about 75% insoluble in water. So it's things like cellulose. It's not actually cellulose, but things like that, big molecules that will not dissolve in water no matter what, kind of like that Twinkie, okay? So 74, 75%, it will not dissolve. Green coffee beans are about 1% caffeine. Right? That's very water soluble, that comes out. And the rest of it is water soluble flavor components. Things like acetic acid, things like hydroxymethylfurfuryl, things like the melanoidins, those chemicals I mentioned earlier. Okay? And so to characterize the mass transfer for coffee, there are 2 key metrics. Okay? The first one is something called the percent extraction. And this is a measure of, it's also known as the yield. It's a measure of how much of the solid phase did you rip out into the liquid phase. All right? And so, like I said, it's maximum 25 to 30%. Okay? The other measure is the total dissolved solids. This is what you drink. Okay? And so the total dissolved solids in a cup of coffee is about 1%. So a cup of coffee, even if it's really, really jet black, very dark, it's still 99% water. Okay, 1% dissolved solids. And so we can invoke the idea of conservation of mass and do a mass balance. And so the mass of coffee solids in has to equal the mass of coffee solids out. As chemical engineers, you should be used to doing mass balances, right? And so here's the main idea. When you're doing a pour-over style brew, you know the mass of dry coffee grounds that you put in. And if you put in that much solid, okay, then you have to get that much solid out. And it comes out in 2 places. You have the unextracted solids. So that's 1 minus the percent extraction over 100 if it's a percentage. Okay, so that's basically what's left behind in your spent moist grounds. And you have your dissolved solids in your cup of coffee. And so the key idea is the blue box has to equal the green box plus the red box. And if we do that and rearrange, we get in what's in the coffee industry a very important equation. The percent extraction equals the total dissolved solids times the ratio of the mass of the brew divided by the mass of the dry grounds. And so here in this equation, we know the mass of the dry coffee grounds. The mass of the brew is how big the brew is. And you don't necessarily know that ahead of time. Okay? And so how do we figure that out? Okay? Well, here's, going back to my class, this is a very important question. Okay? And so for the design competition, right, they have to make a very specific mass for their brew. And so, very specifically, our carafes fit almost 1 kilogram of coffee. We require them to make exactly 0.975 kilograms of coffee. They have, during the competition, we ring a gong. We have a gong, we ring that. Then they have 45 minutes to make 0.975 kilograms of coffee. And so if they mess up, if they don't do that, right, then this is what happens, okay? If they make too little, right, they get a large penalty for not making enough coffee. And the reason for that is, remember, our competition is best tasting coffee, least amount of energy. And if you want to minimize your energy, the easiest thing to do is like not make any coffee at all. To say, hey, I made zero energy, right? And so we require a minimum amount, we give a big penalty, and then the groups, that's what they look like, okay? So if they mess up in the other direction and they make too much, okay, they're also unhappy babies, okay? Because why? Well, they wasted too much energy. They spent energy heating up water, okay? And they just wasted energy. It's no good. And so you guys, you look muy inteligente. So what do you think is in the middle? What's in the middle? Huh? Happy baby? Not just happy baby, happy graduation baby, okay? Right, so you want to get it just right, okay? So how do we do that? How do we predict how much coffee we're going to get, okay? And so again, I think you guys all know this, general conservation ideas. Just in more general, I just used one. I just used in equals out, okay? When we're doing a mass balance, mass is neither created nor destroyed. Here we do steady mass balances, so we don't have to worry about complicated calculus. And so we just have in equals out. And so if we put 100 grams of water into our coffee brewer, we have to get 100 grams of water out, okay? And so that sounds easy until you start keeping track of it. So here's our Mr. Coffee. Here's our control volume, okay? And we know how much water we put in, okay? We can measure that. So we put in the coffee grounds, we put in the water. And so let me ask you guys, how many material streams with water leave the Mr. Coffee? How many streams leave? How many of you guys have brewed coffee before? Anybody here ever made coffee besides Professor Molina? Okay, so where does the water come out? Where does the water come out? Anybody brave? Who wants to guess? Nobody wants to guess? Nobody brave? Necesita más café? Well, there's at least one stream, right? Because you're drinking coffee. That coffee, unless you really made a mistake, the coffee should be wet, okay? You're drinking that, so there's one stream. Where else does water leave? Vapor, yeah, you see vapor escaping. And what else? There's one more. One more. After you're done making the coffee, you should take that basket out, and what do? You throw something away, right? What is that? In English, we call that the spent moist grounds. Moist means humido, so it's wet. There's water. There's water left behind in those grounds, okay? So there's three streams that come out. The coffee that you drink, the steam that escapes, and the spent grounds. That means used grounds. They're wet, okay? So some water leaves there, okay? And so mathematically, what does that mean? We have one known. We know the mass of the water that we feed in. And then we have three unknowns: the mass of the water in the brew, the mass of the water in the grounds, the mass of the water in the steam, right? And so now what we can do is make some engineering simplifications, okay? And the very first one is, let's assume that the amount of steam is negligible, okay? That the mass of the water that evaporates is much, much less than the mass of the water in the feed, okay? And so that might sound strange because you can see the steam. You see steam escaping. It turns out that even though you can see it, it's very small, okay? And you can actually measure it by doing a difference approach, and you can show that it's negligible. Okay, so that means we cross out one of the terms. So we went from 3 unknowns to 2 unknowns. So we're making progress. The second assumption is that the brew is mostly water. So mass of the water in the brew, that's just the water, not the solids. But like I mentioned, a cup of coffee is 99% water. So we just approximated that as being the mass of the brew. Okay? But then the third stream, this is more complicated, right? We have to know, well, how much mass do we have in the coffee grounds, the spent coffee grounds? Okay? And so here we have to invoke an empirical observation. And here is a thought experiment. Okay? So let's imagine you have your sink and water dripping out. and you take some paper towels, dry paper towels, and you hold the paper towel, like this guy, underneath the sink. And what happens? The water comes in, and it absorbs into the paper towel. Okay? And if you sit there long enough, eventually the paper towel fills up, and the water starts dripping through. Okay? So in other words, the paper towels have a finite capacity for water. They can hold some water, but not infinite water. Okay? And so mathematically, we would say that there is something called an absorption ratio. This is a dimensionless number. It's the mass of absorbed water per mass of dry paper towels. And you can imagine that if you take twice as much paper towel, you can hold twice as much water before it spills through. And so my claim to you is that coffee is exactly like a paper towel. Coffee grounds also absorb water and also only absorb a finite amount. So there's a certain mass of absorbed water per mass of dry coffee grounds that you put in. Okay? And we call that the absorption ratio. And so then if you take that, you take this idea, the absorption ratio is equal to the mass of the water in the spent grounds divided by the mass of the grounds. If we rearrange that, we can then substitute this into our equation. Boink. Here, that's a lot of fun. Let me do it again. Boink. Okay, right? And so now we went from 2 unknowns, and now we just have 1 unknown. Okay? And so now we have a predictive equation. Let's rearrange it, and this is a very useful predictive equation. What does it say? It says how much coffee we get to drink is equal to how much water we put in minus something. And that something is proportional to the mass of the coffee grounds. And so oftentimes students in the class, they'll say, oh, my coffee is not strong enough. Let's put in more coffee grounds. We'll make it stronger. And you can do that. It works. Your coffee is stronger. But what is this telling you? You're going to get less coffee to drink as a necessary consequence of putting in more grounds. I also tell students that they might not recognize this, but they studied this equation in high school. Did you guys study this equation in high school? So at least in the States, we often talk about y equals mx plus b. Do you guys do that in high school here? Y equals mx son b. Mi español es muy tonto. Lo siento. Okay. Right. So anyways, this is a y equals mx plus b. This is a linear equation, okay? And so if you go and do some experiments where you plot the mass of the brew, right? That's the vertical axis, versus the mass of the grounds that you put in, that's the horizontal axis, it says it's going to be a straight line, okay? The slope of which is the absorption ratio. And so this is a beautiful experiment. In half an hour or an hour, you can do a whole bunch of different brews, get these data, learn about linear regression, learn about fitting experimental data to a model using coffee. And this is an example of student data where it's just, you get a beautiful straight line. Okay? Going back to our original question, which is thinking about coffee, we can now combine our solid mass balance and our water mass balance, and I'll go quickly through this. Basically, we get a very nice dimensionless equation. The percent extraction is equal to the TDS times your brew ratio. You control that. That's how much water per grounds you put in, minus your absorption ratio. And it turns out that this equation governs these diagonal lines in something called the coffee brewing control chart, which relates the total dissolved solids to the percent extraction with different brew ratios. That's the ratio of coffee grounds to water. And it turns out that I'm not going to go into detail, but there's sensory information that people have put together that tells you how it tastes as a function of the extraction and the TDS. So what that leads into, though, is a very, at least for engineers, what should be an obvious question. Well, wait a second, I can control the brew ratio, because I control that. The absorption ratio, that's a constant you can measure. Coffee grounds have an absorption ratio. It turns out it's about 2.1 grams of water for every gram of coffee grounds. How do I predict the TDS, right? Because where's the prediction for that? And so what that means is we'd have to go into a more detailed model with calculus. And so I can do that if there's interest. Should I go into that? How are we doing on time? You guys ready for calculus? Who likes calculus? 7 more minutes? Oh, very fast calculus, okay. So let me switch to, oops. Oops. Oh. Oh, here we go, calculus. Okay, so here's some handwritten notes, okay? And so I guess I'm gonna have to stand over here. So, okay, here's the question, okay? So we have a coffee brewer, okay? There's my bad picture of some coffee grounds and some water. And here's our question. We wanna know what's the simplest chemical engineering model that captures how quickly mass moves from the solid phase to the liquid phase. And so here is a picture of our control volume, okay? Can you guys see the mouse? Let's see, maybe not. Can you guys see the mouse? Yeah, so here's our control volume, right? And basically the control volume is gonna be everything that's liquid in there. So it's gonna exclude the solids. And so our approach, we're using that geometry is something called a clever coffee brewer, okay? And what we're gonna do is we're gonna make a bunch of simplifying assumptions. We're gonna imagine that you're stirring this thing so it's well mixed, okay? So there's no spatial gradients. And we start with our general conservation equation. Our accumulation of solid phase molecules equals what comes in minus what comes out plus any reactions, okay? And so here we're interested in the total dissolved solids. We're gonna neglect any chemical reactions. We're gonna neglect any evaporative losses of VOCs, that's volatile organic compounds, okay? When you brew coffee, you can smell it. When you smell it, what is that? That's molecules that have escaped from the solid phase into the liquid phase into your nose. We're gonna ignore that too. And so basically what that means is that we have accumulation, okay, of molecules in the liquid phase equals the rate at which they move in from the solid particles into the liquid. And so here's a little calculus. So what is the accumulation? Well, here we go. It's the time derivative of the integral over the entire volume of the liquid times the concentration C, okay, integrated over that, right? And if it's well mixed, so again, we're mixing it, there are no spatial gradients anywhere, then we can pull this out of the derivative and we get that it's just this. It's the volume of the liquid times the time derivative of the concentration. And the volume of the liquid is related to the porosity times the overall volume. Okay? Okay, and so, so that's the accumulation. It's just dC dt, okay? This comes back to our mass transfer coefficient. And so here I call that K sub C. Here's our concentration difference. Here's C near, and here's C far. And A is the area, the overall area of the coffee grounds. And so we already talked about mass transfer coefficient. We talked about this, yes. So we're using this mass transfer coefficient approach. Okay. And so the general mass balance then is the accumulation, okay, equals this flux in, right? And so if you've studied this type of problem before, and hopefully most of you have, you're seeing what we're doing is we're building up a first order linear ordinary differential equation. And so what we can do then is rearrange this. We have an initial condition at time equals 0, the concentration equals 0. Okay? We do some simplifications, okay? And we get this very nice little equation, dC dt equals our mass transfer coefficient times little a, and we've just tucked a bunch of the constants. We have our surface area to volume ratio and the porosity captured in A. Okay? And so now, all right, hopefully you guys have done this type of problem before. We have, again, it's a first order linear ordinary differential equation. We separate the variables and we integrate, and long story short, we get this nice little boxed equation. We get that the concentration, okay, as a function of time of our dissolved solids is equal to some saturation concentration times the product of 1 minus the exponential function of the negative of this mass transfer coefficient times time, okay? And this is a very classic result, right? When you plot this, what does it look like? It looks like this, okay? So initially, it increases linearly, okay? But then eventually it plateaus. And so that's the model prediction. It turns out that there's lots of complexity associated with this. And so one of the things that we do in my class at Davis is we try to measure this, and if you do things correctly, you can actually get data that looks like this using the Clever Coffee. I guess I'm with Professor Molina. I'm leading a workshop this afternoon. We're going to try to test this equation using some French presses. What time? 10 o'clock. A las 10. Okay. So, even better, coffee in the morning. Me gusta. Okay. So we will, for those of you who are joining us, we're going to test this equation, see if it's any good. Okay. All right. So that pretty much brings us to an end here. So what I've tried to do is show a little bit about what we've been doing at UC Davis, how I got into coffee, okay? There's lots of complexities going on. These are phrases you guys recognize. You know, I simplified things. In reality, it's not isothermal. In reality, it's not well mixed. In reality, you do have to take into account off-gassing, especially for fresh coffee. You really do have to take into account water chemistry effects. And then finally, the whole point of making coffee is you want to enjoy the taste. And there's a whole other discipline of sensory analysis that really analyzes how do people taste the coffee. Different people like different things. And here's a couple of my students working on stuff, a graduate student and a postdoc doing different projects. But I think I'll finish here. I'd like to thank Professor Molina for inviting me. He's been implementing a coffee class here. I'm very flattered and honored that people in Colombia think about coffee and think about teaching chemical engineering with coffee. And so thank you very much for your attention, and I'm happy to take questions. Preguntas? Sí, señor. Much, yeah. I mean, so typically, his question was, how much flavor do you lose every time you brew over the coffee? Yeah, so coffee is, like I mentioned, it's about 30% soluble. And the first time you brew, you rip out 20%. So the next time you brew, there's only 10% left, and that's the stuff that does not taste good, right? So that's why you never reuse the spent coffee grounds. I mean, you can, but it's not going to taste very good. Good. Pregunta bueno. Yeah, okay. Más preguntas. I couldn't quite understand. Stand up and say it loud. I couldn't hear the keyword. Is there a restriction?
The type of flavor. Everyone.
Oh, okay, very, very good. Yeah, so let me go back. Yeah, most people are unaware that coffee can have some of these amazing flavors that I was describing, okay? And so this is the Coffee Taster's Flavor Wheel, okay? There's a similar flavor wheel for many different food products. The most famous one is vino. Vino wine has many different flavors, okay? I don't know, if you come up later, I can show you. There's many words on here: chocolate, cinnamon, nutmeg, smoky, okay, ashy, things that you don't want, rubber, petroleum, okay? All these flavors are present in coffee, okay? And I don't know if you can get any flavor, but many of them are here. Even potato, papas, potato flavor, that's a defect in coffee. And why they occur is because green coffee beans have very complicated chemistry, and then when you roast, it's even more complicated. So there's something about somewhere between 800 to 1,000 different types of molecules that contribute to the aroma and the taste of coffee. That's even more than wine. So coffee is even more complicated. And so in los Estados Unidos, high-end cafes, they pride themselves, they're very proud if they get a coffee that has, for example, tremendous strawberry aroma, fresas. Las fresas, strawberries, yeah. So, fresas y café, delicioso, right? So that happens. And and that's why they can charge a lot of money for those. Good question. Yes?
Yo voy a preguntar, pero la que va a traducir es... Bueno, entonces...
Buenas.
En las pruebas que ustedes hacen, ¿qué nivel de torrefacción usan en el café? ¿Y qué tipo de agua usan en el café para hacer las pruebas? Y aparte, si solo han trabajado con arábigos o han trabajado con robustas.
So, robusta.
Arábigo y robusta.
Yeah, no conozco robusta, pero do you ask about agua, the type of?
Robusta son las especies que se usan
I know robusta, but what is the question? Yeah.
Torrefacción.
Torrefaction with con sucre.
Genial.
Azúcar. Yeah. So I think multiple questions. So yes, water chemistry, very important. Okay. If you brew with distilled water, the coffee is very flat, very dull, no good. If you have very high ppm, parts per million of dissolved ions, then it is salty and chalky. What's also important is the relative ratios of different ions. So if it has lots of magnesium or lots of calcium, even at the same ppm, that matters. And so at the coffee center, we have deionized water that we add very specifically certain amounts of ions, so we control that. Okay. For Robusta, yes, we're also very interested in Robusta. For those who don't know, about 2/3 of the coffee in the world is Arabica. Colombia makes very good Arabica coffee. About 1/3 is Robusta. Arabica is good and expensive. Robusta is cheap and does not taste very good. But they use Robusta because it has lots of caffeine, and it's good for instant coffee, soluble coffee. So I'm not sure what your question about Robusta was. But then for torrefaction, some places like España y Italia, they roast the coffee with sugar, all right? And usually, my understanding is that usually they take poor quality coffee, add sugar, and roast it. It gets a little bit of those sugar roasting Maillard reactions. It maximizes the Maillard reactions. Did I answer your questions? Okay, gracias. ¿Más preguntas? Okay, muchas gracias.
So thank you, William Ristenpart. Thank you. So now we will have a presentation for sister chapter from University of Michigan. They are going to talk us about applying to graduate school in the United States.
Hola a todos. Yo soy Fritz, y I am the president of our student chapter at the University of Michigan.
Hola, me llamo Según y soy el vicepresidente de nuestro capítulo.
Hola, me llamo Alex White, soy el secretario de nuestro capítulo.
Y yo me llamo Elaine y yo soy mentorship chair. Sí.
First of all, we would like to thank you guys so much, especially Professor Molina and the members of our sister chapter that invited us to come to this conference. They were at our national conference as well, and we really appreciate the opportunity to come out and just be able to be here in Columbia with you guys. And so with that, we're going to do a little bit of an introduction to our presentation and just explain what the University of Michigan is like and what we do at our college there. And then also going into that after the introduction, we'll be explaining some of the necessities about applying to American graduate school and why it's a great option. So with this, the University of Michigan is in the opposite side of the United States of California. We are all the way up in the north where the star is on the graph, and California is on the west coast as there's also no direct flights from Michigan to here, so we stopped in Florida, which is in the very southeast part of the United States. And yeah, this is where our school is also. So a big part of our campus is American football. So on every single Saturday, this is the second biggest stadium in the world. There's 115,000 people that fit into this stadium, and we play American football in there, which is different than soccer, obviously. And so there's also days full of tailgating, which is where all the students go and hang out outdoors all day before the football game. And yeah, these are some other parts of our university as well. So the Law Quad, which is an area that actually they were considering filming Harry Potter in this part of our campus. There's a lot of old architecture, but J.K. Rowling wanted to film it in Europe, in Britain specifically. Yeah, and so then also this is our diag, which is our main part of our campus, our central campus. So a lot of students are walking through here all day, and it's very busy, but it's a nice open air area for our campus. And so a little bit about our AIChE chapter too, our AIChE chapter. So our events, our primary thing that we do is every single Thursday, we host a luncheon. And so with this, we have a company come out from all sorts of different industries of chemical engineering, and they explain how a chemical engineer fits into chemical processing, our pharmaceuticals, or the food industry. And you get a better idea, especially as an underclassman, of figuring out how can I fit in as a chemical engineer and what are my opportunities once I graduate. Then we have plant tours, which are really important. This is critical because it's one thing to get told in a presentation, all the opportunities that you have, but it's another thing to see people actually doing those jobs. And so we do typically about 5 or 6 plant tours a year, which Elaine organizes as part of mentorship. Finally, we have our social events where we go do trivia at local restaurants and yeah, and so and all sorts of events. We go to cider mills, which is yeah, and so all sorts of things like that. Then our mentorship program, which is what Elaine is also in charge of. So what this is and what kind of makes a little bit, this is something that our chapter does that's really unique, is our underclassmen have an opportunity with our upperclassmen to get paired up and help explain what are some of the things that they've learned going through our program. And then also you can get paired up with industry mentors as well, people that are actually out there in your field doing things that you're interested in, and you can connect with them and figure out if this is something that you're actually interested in as well. And so that's pretty much just a little bit about us. But now going into the other part of our presentation about applying to a PhD. And let's start off first of all with what can you do with a PhD? Why should you go through a lot of effort and time to go get a PhD? And so according to Stanford University, 2/3 of people go into applied research once they get a PhD in chemical engineering, and the other 1/3 go into teaching research, which is approximately how it breaks down. And so you can go into applied research, and with this, chemical engineers go into so many different fields, which I'm sure you guys have seen from all your friends that have graduated from school. There are so many different industries you guys can go into. But right now, obviously, with information technology being huge, that's a big field that people are going into. There's biotechnology, of course, chemical processing, and it really is impossible to break this down into just one category. PhDs can go do research in any sort of field, and you have the background once you have a PhD to attack any sort of topic. And so in many of these fields, something that's really important to note is you can be a part of a research team without a PhD after an undergraduate degree. That's entirely possible, but if you want to actually be directing your own research and effectively making change in that area more, you're really going to need a PhD to make impact and affect change in that area. And most critically, so you're going to be doing a thesis if you do a PhD. And so if you're really passionate about one topic and you want to just become a subject matter expert in that, a PhD is definitely the way to go because you're going to get a lot of knowledge in that one topic area. You're going to be going with an expert faculty member in that area too and be learning from them for 4 to 6 years. And so a little bit more about the other part that you can go into is teaching and research, which this is what approximately 1/3 of people go into. And really, again, chemical engineers can do anything, but this is a big area that chemical engineers especially are interested in going into. And so most schools in the United States at least require that you need a PhD in order to be a professor there. And so a PhD enables you to direct your own comprehensive research on the side of this. Some people, when they get a PhD, just focus on teaching, and that's perfectly valid too. But also, if you're interested in dedicating time to also research, this can be a great option. And then, so a little bit about just what it takes to get a PhD if you're not familiar. So this varies in time depending on the university and depending on what your thesis matter is. But a typical range is between 4.5 to 6 years to complete a PhD in chemical engineering. It varies based on what you can do after an undergraduate in chemical engineering. You can get a PhD in other subject matters as well, like material science, mechanical engineering, and other topics. But for chemical engineering, this is a typical time range. And then typically upon entrance, you'll be paired with a faculty member in your first year. And so with this, it varies based on the schools. For us, in your second month at the school, you'll be paired with a faculty member, but it can range to up to a year where you'll do rotations around different laboratories and try and figure out which faculty member did you align with the best, connect with their research. And one thing that I think you shouldn't be worried about, though, is that if you apply to a research that is doing a fair amount of research in your area, you will get paired with a laboratory that is in your area of passion. They're not going to over-admit students that they're not going to admit 60% of their students that want to study energy and only have 20% of their faculty doing energy. They're going to admit students based on their interests and make sure that you have an ability to get paired up with who you applied to get into the university with. And so a typical workload on top of your research that you're going to be doing every single semester is, because you're still taking classes, is you're going to have about 3 lectures per semester and a seminar. This is pretty typical at our university, at least. And so you do also have a full course load on top of all the research time that you're doing. So this is a very busy time of your life, but if there's a subject matter that you're really passionate about, it can be really fulfilling and worth it. And then finally, so last years of college, I discussed your first year, you're going to be pairing with the faculty. However, the primary point of a PhD is to develop a thesis in conjunction with a faculty member. And this can be one of the most fulfilling experiences of your life, to really have that mentee-mentor connection that's very deep. And this can be one of the best opportunities that you possibly have. And so with this, I'm going to pass this off to Segin, who's going to talk about the admissions timeline.
Thank you. Hi, so now I'm actually going to talk about what you need on paper to apply to for a PhD program. So right here we have an actual list of all the things you'll need and some things that are very highly recommended as well. So just to go through, we have first the undergraduate record. So that's usually just a transcript and sometimes a class rank if that's available. So you'll have to submit that as a part of your application. And then on top of that, you'll have to take a couple of different exams. In the case of international applicants, you will need to take both the GRE and the TOEFL, which I'll talk about in a later slide. And then you'll also need a different number of letters of recommendation depending on the colleges that you apply to, and then a statement of purpose and personal statement, which are 2 separate things that we'll discuss further later on. And then there'll be an application fee associated with almost every application you fill out, as well as visas required. And research experience, although it's not required, is very highly recommended. And adding your resume or CV, is also usually very helpful as well in the application process. Okay, so here I kind of just want to talk about some of the maybe cutoffs that you think of in terms of scores when you're submitting your application. So listed here we have some of the typical scores of the accepted PhD students at the University of Michigan that we've seen. So for the GPA on a 4-point scale is usually about a 3.8. And then on the GRE, or the graduate record exam, we usually see students scoring in these areas with, or here, I'll go through first the categories in case you're not aware already. So the GRE is usually divided into 3 different sections, that being the verbal reasoning, quantitative reasoning, and analytical writing sections that all measure different aspects. And you'll need to score at least these numbers, so 155 for the verbal reasoning, which measures essentially your text comprehension skills, and then a 165 in the quantitative reasoning, so that's more of logical and mathematical type questions, and then the analytical writing measures your ability to communicate critical thinking, and you'll need at least a 4.35 in that category as well. And then to talk about the TOEFL, that stands for the Test of English as a Foreign Language. This exam essentially tests your proficiency in English and whether or not you'd be prepared to study at an American university where you'll be learning everything in English. And so for that, you'll need these minimum scores as well for general admission into PhD programs. And now we have here a admission timeline to give you a general idea of what to expect when. So this is specific for the University of Michigan, but most universities in America follow the same timeline. So by December 15th is when the actual PhD applications are due, and then a month later is when master's applications are due if you're interested in that instead. But throughout January is when the actual colleges will start collecting and reviewing all of the applications, and by early April is when they'll start sending out the first offers of admission and financial aid to international students. And by February and March, master's admissions will be offered as well. And after that, in early April, we'll have final admission decisions will be mailed to all applicants, and then by then you'll be given time to make your decisions. And April 15th for Michigan and for most other schools is the due date for all outstanding admission offers and decisions. And so now to talk a little bit about the recommendation letters that I mentioned earlier. So recommendation letters are a huge part of the application process. This is really what essentially talks about you outside of all of the scores and everything else that you submit. This kind of paints a picture of who you really are outside of your essentially how you're perceived by everybody you work with, which is a huge part for the university to get to know you when they're trying to admit you. And so these recommendation letters should be from a professional source, in most cases either a professor or lecturer or researcher that you work under. And so it's usually better to opt for somebody who knows you very well over somebody with just a very high reputation, who's very well regarded. So we would usually suggest, as an example, say you want to ask a professor maybe that you got a worse grade in their class, but who knows you very well because maybe you went to every single office hours and lecture and everything, and you spent a lot of time with them, and they can write a much better letter about how you worked and how great of a student you were versus maybe a class where you got an A+ in, and that professor has very good reputation overall, but they might not be able to write as well about you. And so that's something that you definitely want to keep in mind when you're asking different people to write your letters of recommendation. And when you do ask these people, you want to share with them which schools you're applying to and essentially what kind of topic or projects you're interested in what types of projects you may be interested in at those schools, so they have a better idea of how to tailor this letter for you. And then also just give them plenty of time to actually write this letter. Usually anywhere between 2 weeks to a month should be sufficient, but yeah, just be courteous and polite about that. And so now I'm going to pass this off to Elaine. You got that. Perfect.
So as Segin was saying, there's a few parts to your application, and two of those are your statement of purpose, which I'm going to talk about first, and then your personal statement. So they're both a little different, but they're both like your opportunity to talk about yourself to the person reviewing your application. So in addition to your letter of recommendation, which is from like a professor, you're able to write something as well that is your way of letting that person get to know who you are. So the first being the statement of purpose. And this is a description you'll write about yourself that includes your experience, like professionally and through research, the things that you were involved in during your college experience, and also what you're interested in that school. So this is where you're able to say what field you might be interested in, what you would like to study, possibly what faculty you're interested in at that university. And then you can also tie in all of your research experience, your possible internships you might have worked at, and really talk about like the type of field, where that passion is, and then describe where you want to go from there, which is a great opportunity to like kind of expand. Like, let's say they ask for your resume, but obviously you only get to write like 2 bullet points under each experience, but this is where you can really write like a lot more and expand on all of those topics. However, you don't want to go way back into like your childhood. So I said, like, do not write like a long biography. This is actually a place just for like kind of your college experience, your professional experience, and your personal statement is where you can really talk about how you got to where you are now. So in contrast, your personal statement is a place where you can really help that application reviewer get to know you. So you want them to understand your personality a little bit, understand what made you who you are today, and then like what developed your passion. So for example, let's say you're applying to a program in medicine. This is where you could say, oh, well, as a child, my grandpa was very sick, and I always wanted to be able to help him. And so now you have this passion for medicine. This is like your opportunity to really tell them what developed that passion, why you are the person you are today. As well as this is a great place to discuss any challenges you've overcome. Let's say that you had like one bad semester. Maybe you had a family issue or a medical issue, and so your grades that semester were really low. This is your opportunity to like tell the reviewer what was going on, and so then they won't hold that against you. They can say, oh, well, they were doing so well, and then they didn't do well, but now I know why. And then that'll help you in terms of getting accepted into the school. In addition, you can go a little bit further back. You can say, oh, well, I started liking science when I watched the clouds outside, or when I started tutoring students in your elementary school or middle school, helping people with math, and you can really go way back and start telling like the full story of your life. However, you want to keep this like very personal. Don't try to include too much of like your like research like findings. Keep this more just about your personality, yourself, and your experiences. And furthermore, when you're writing a personal statement, you want to just kind of start off by listing all the topics that you think might be something you want to include, because it can be kind of a daunting task to start writing this paper. So if you start by just listing them all out and then kind of tying them together into the story that you want to tell, and then coming up with that central theme that you would want to convey. Great questions to consider. Things that you should try to answer in your personal statement would be, what makes you unique? What makes you different? Help that reviewer really get to know you. Why did you have an interest in the field? You want to show them that you're not just applying to this field to just out of no reason or to make money or something. You want to tell them like why you're like truly interested and want to learn more about that topic. What motivates you is a great question as well. And then lastly, when you're revising your personal statement, you want to make sure that since this is a kind of a picture of who you are, you want it to be very well written. Check for grammar. Make sure you're following their page limits, their font size, their margins. You don't want any of those little technical errors to be held against you. And then have friends, have faculty, have your family read over it to just make sure it's a really solid paper. Moving on, I'm going to pass it over to Alex.
Okay. With that, we've gone over the application process, and now I'm going to talk a little bit about how do you decide where you actually attend school. So I'm going to be going over researching schools and labs. So the primary thing you want to be looking at when looking at schools you're attending for your PhD is what research do they do at that institution? Do they make sure they are doing research in your field that you are interested in? Because some universities will offer expertise in a field that others may not. So also look into what is the structure of the research group that you are interested in, and do you think you will thrive in that structure? And also, what are the teaching requirements and opportunities for graduate students? Some schools will require you to teach as a graduate student instructor, while others might not. If you want to go into academic research and teaching once you have your PhD, you're going to want to look for programs that offer this opportunity. Other schools might not offer that, and so definitely tailor your school to the experience you want. And then also look into what faculty members would you like to work with. You're almost guaranteed to work in the field that you desire, but you're not necessarily guaranteed to work with a specific instructor. So make sure the institution you're looking at applying to has at least 3 or 4 professors that you would be interested in working with. Going on, so that the research that the institution does is probably the most important thing you can look into when applying, but also make sure to look into what does the school have to offer. So graduate school is quite costly in the United States, so make sure you look into what financial aid packages they offer for graduate students. Also look into what facilities and resources the institution has, as this will vary from school to school. And what is the reputation of the school? This is generally more important if you're planning on doing academic research and teaching once you receive your PhD. And so consider that a little more heavily if that's what you want to go into. But if that teaching is not necessarily for you, then you primarily want to focus on the research that the school does. Gracias. All right. So beyond what the school has to offer you and the research that the institution does, you want to look at, can you see yourself living there? What does the city have to offer you? What do the class sizes look like? If you're a person that thrives in a smaller class setting and you're looking at 2 universities that are quite similar in your mind, but one of them offers smaller classes, you probably want to go with that institution. And then moving forward, if in your research you find that you have a question for a professor or a graduate program coordinator, you want to adhere to these points on the board. Any general questions about the program and the application process, you're going to want to direct those to the graduate program coordinator. Whereas you might find that in your research you have a very specific question you want to ask a professor. If that's the case, adhere to contacting them via email as opposed to a phone call, because it'll give them a lot more time to think about your question and respond in a time that suits them. And that way you don't end up playing phone tag and missing calls and leaving messages, and that's just a more confusing method of communication. Also, if you are contacting a professor, you definitely want to make sure you are very familiar with their research and you have a specific question about what they study, and definitely show that you want to learn more. What you don't want to do is email every professor at a university saying you're interested in their research. Our undergraduate advisor at our school actually sometimes receives emails saying, "Oh, Dr. Montgomery, I'm very interested in the research you do and I would love to learn more." But she does not do research, so you definitely do not want to be that person. And so yeah, definitely make sure if you're emailing a professor, you're not emailing every professor at the institution and you have a very specific question and you are well read on their research. And with that, we want to thank you guys so much for listening to our presentation. Thank you for the student chapter, our sister student chapter, for inviting us here, and Professor Molina, wherever you may be, for hosting this amazing conference. And now we'd like to open it up to any questions you have about the University of Michigan, our chapter, applying to graduate school. And we do encourage you to ask questions in Spanish if that's your preference.
Hi, my question is, you can tell me a little bit more of the financial aids or scholarships, but you know that here the price of college is low, expensive than you say.
So the one thing that's nice about a PhD as opposed to undergraduate is that it typically is significantly more funded due to the fact the amount of work that you're doing for the university. You're doing research that's extremely helpful and provides a lot of funding for these universities, especially in America. So PhDs, especially in the subject matter of chemical engineering, tend to be significantly more well-funded than undergraduate education grants. And so it's a little bit hard to tell because a lot of these places, they list a price that is substantial. It's very high for international students. However, by the time you actually get financial aid, it ends up being a lot more affordable than you would expect in the United States because they subsidize it heavily with grants, especially for chemical engineering PhDs.
Any question?
Thank you so much
Yeah, no problem.
for the
No problem.
presentation.
Thank you.
The presentation, you give me.
And if you have any other questions that you want to ask us individually, not in front of everyone, we'll be over here. Thank you.
Bueno, chicos, vamos a darles unas pequeñas instrucciones para que me pongan pues mucha atención. La idea es que vamos a hacer una fila muy ordenada al salir. Van a darles una camiseta, de acuerdo pues como a la talla que eligieron en un formulario que diligenciaron. Luego van a recibir una almojábana y enseguidamente las personas de los workshops van a estar divididas para que las personas pues se puedan dirigir. Tenemos que hacerlo un poquito veloz porque pues ya estamos como sobre el tiempo. Calma, esperen, les termino de